Mars is far away. Really far away. Light takes 3 minutes to get from Earth to Mars on closest approach, but getting humans there requires traveling 400 million kilometers on a curving arc around the Sun. For comparison, the Moon's only 400,000 kilometers away, so you have to travel 1,000 times further to get to Mars.
It took 3 days for the Apollo astronauts to reach the Moon, so would it take 3,000 days to reach Mars? Thankfully, no.
The Apollo astronauts traveled between the Earth and Moon at a geocentric velocity of 1.5 kilometers per second. This velocity wasn't set by the constraints of the rocket technology at the time, but instead by the mission geometry. The Saturn V could have rocketed the Apollo astronauts to the Moon at 3 times that speed to reach the Moon in a single day, but there would have been a price to pay. They wouldn't have been able to stop. The Moon has a relatively weak gravity and no atmosphere to slow down against, so the Apollo missions had to rely entirely on propulsive deceleration. Mars, on the other hand, has a substantial gravitational pull as well as an atmosphere, both of which can assist in facilitating a deceleration maneuver. This means a spacecraft can reach Mars with a much greater approach velocity and still manage to capture into orbit and land. More importantly though, a spacecraft leaving Earth's sphere of influence can benefit from an extra boost of 30 kilometers per second due to Earth's orbit around the Sun.
So, although Mars is much further than the Moon, we can travel there at 20 times the speed. The journey still takes much longer though, and requires significant planning.
Keep in mind that Earth and Mars are constantly changing their positions relative to each other. This means you have to launch at the right time, known as a launch window, to ensure Mars will be there to greet you when you arrive at its orbit. When exactly a launch window occurs depends on the specifics of your mission architecture, but in general, a launch window to Mars opens every 26 months. When planning a round-trip mission, there are basically 2 different flight plans, known as the long-stay conjunction mission and the short-stay opposition mission.
Let's take a look at the pros and cons of each. The long-stay mission is the lowest energy mission to Mars, especially when a Hohmann Transfer is used on the way there and back.
A Hohmann Transfer is an orbital maneuver that typically requires the least energy to change orbits around the central body. The right time to launch for a Hohmann Transfer to Mars is just before closest approach, when the phase angle is 44 degrees. The Hohmann Transfer takes 260 days to get to Mars, and leads to a stay on the planet of 500 days. After spending another 260 days in space on the way home, the total time spent away from Earth is approximately 1,020 days.
That's almost 3 years. Given such a long total mission duration, some of the more risk-averse voices at NASA prefer the short-stay mission, since it reduces the total mission duration to just under 2 years.
To make this possible, the outbound leg of the journey uses additional propellant to get to Mars in just 180 days. Once there, instead of waiting 500 days for a minimum energy launch window back to Earth, the return home begins after only 30 days on the surface. Since Earth and Mars aren't yet in optimal positions, the return journey has to fly by Venus to get a gravitational slingshot back to Earth. This results in a return journey lasting 430 days. But since significantly less time was spent on Mars, the total mission duration is still a few hundred days shorter. That being said, it's been argued by many that the advantages of a shorter mission duration are overshadowed by the significant reduction in time spent on Mars, the increased time spent in transit, and the much larger propulsive requirements needed to fly by Venus.
It's ironic that the main perceived benefit of the short-stay mission is safety, when in fact the long transit times maximize the risks associated with space radiation, zero gravity, and transit life support systems. Being closer to the Sun during the Venus flyby will add extra strain on the heat control systems, and the extra velocity from the slingshot maneuver will make aerobraking in the Earth's atmosphere a lot more dangerous. Not only does the short-stay mission expose the astronauts to the greatest in-space risks, the larger propulsive requirement results in a transit vehicle with the least mass budget to put towards system redundancy. If you're looking for reasonable propulsive requirements, a long stay on the Martian surface, and short transit times, there's a third option to consider.
With a little extra propulsion during transit, the travel time of the long-stay mission can be dropped from 260 to 180 days or less for each leg of the journey. This results in a Mars stay time of 550 days and a total mission duration of about 910 days. This long-stay 6-month transit architecture is strongly favored for human missions, since it minimizes crew exposure to the in-space environment while maximizing the surface stay time and keeping propulsive requirements within reason. For cargo, the 9-month Hohmann Transfer is favored, being the cheapest and allowing for the largest cargo capacity.
It all sounds straightforward in theory, but how would these transits actually be performed in practice? What maneuvers would be required? How much propellant would be needed? And could a fully functioning Starship actually take us to Mars? To answer these questions, let's go on a journey to Mars together, from Earth launch to Martian landing using SpaceX's Starship as our vehicle. But before we go anywhere, we'll need to understand an important concept in spacecraft flight dynamics, known as delta V.